Let f be a function from the set of natural numbers to the set of natural numbers such that f of n plus 1 is strictly bigger than f of n for every n in the set of natural numbers. Show that f of n is equal to n for every n natural number. By natural numbers, I mean the set of 1, 2, 3, and so on. Let's solve the problem. Suppose, by contradiction, that for every n natural number, f of n is not equal to 1. Since f of n is in n, this means that f of n is bigger than 1 for every n natural number. Now, if we consider a natural number a0 greater than 1, we can consider a1 to be f of a0 minus 1, and this is greater than 1 from this, the star condition. Okay. And now we can build a sequence AK in the following way. The base of recursion is this one, and supposing to have defined AK, we can define AK plus 1, A sub k plus 1, to be f of A sub k minus 1. And again, this is strictly greater than 1 for the star condition. Now, using this hypothesis, we know that f of a sub 0 is strictly greater than f of a sub 0 minus 1, but this is a sub 1, so this is equal to a sub 1. But now a sub 1 is strictly bigger than f of a sub 1 minus 1, that is equal to f of a sub 2. And so we can go on indefinitely, since f of a sub n is strictly bigger, using the same argument, of f of a sub n plus 1. Note that every time note that these logical steps are valid for this hypothesis, because since f of n is strictly bigger than 1 for every n, we know that a sub k is strictly bigger than 1 for every k, and so every time when we have a sub 1, a sub 2, and so on, we can subtract 1 because a sub k is greater than or equal to 2, and so subtracting 1, we are still in the set of natural numbers. Okay, but here we got a contradiction, because what do we have? That this is a natural number, and we can indefinitely continue this sequence, but this is impossible, since these numbers are all bigger than 1. So if this was true, we would have that the set of 1 to up until f of a0 is infinite, but this is impossible. So we got a contradiction from our hypothesis that f of n is not equal to 1 for every n We get that it does exist a natural number n such that f of n is equal to 1. Now we want to prove the following. For every n natural number and for every t natural number, we want to prove that f of t is equal to n if and only if n is equal to t. And we are going to prove it by induction on n. So, first step is the induction basis. So we consider the case n equal to 1, and we want to prove that for every t natural number, f of t is equal to 1 if and only if t is equal to 1. So we want to prove that f of t is equal to 1 if and only if t is equal to 1. Okay, so first of all, we know that an n such that f of n is equal to 1 exists. Suppose, by contradiction, that it is possible to find an n in n such that f of n is equal to 1 and n is strictly bigger than 1. Then this led to a contradiction, because f of n plus 1 is, because f of n, is bigger than f of n minus 1. We can consider f of n minus 1 because n minus 1 is still a natural number. But this is impossible because this is equal to 1, and this, since it is in the image of f, this should be a natural number, but there's no natural number that is less than 1, since the set of natural numbers is of the integer greater than or equal to 1. So this is impossible, and thus we got that the only natural number such that f of that natural number is equal to 1 is actually 1. Okay, now we can go on and assume the inductive step, the inductive hypothesis. Let n be a natural number greater than 1 and assume to be true that for every m in the set 1 n, we have that for every t natural number, f of t is equal to m if and only if t is equal to m. Now we want to prove that, so we want to prove that f of t is equal to n plus 1 if and only if t is equal to n plus 1 for every t natural number. Now we can again suppose by contradiction that for every m natural number, f of m is not equal to n plus 1. So, from our inductive hypothesis, we know that for every m natural number such that m is greater than or equal to n plus 1, we have that f of m is greater than or equal to n plus 2, because since the equality of f of t equal to m for m in this set is true only when t is equal to m, we know that if t is strictly greater than n, so if it is greater than or equal to n plus 1, we must have that it is greater than or equal to n plus 1. But since we are supposing that it cannot be n plus 1, it must be greater than or equal to n plus 2. Okay, now we can play the same game that we played in the first step with this infinite descent argument. Okay, so we can consider a0 to be a natural number greater than or equal n plus 2. We can choose a natural number such that. And now what we know? What do we know? We know that a sub 1 that is defined as f of a sub 0 minus 1 is greater than or equal n plus 2, because we are simply using this fact. Okay, but now, assuming to have defined a sub k greater than or equal n plus 2, we can define a sub k plus 1 to be f of a sub k minus 1, that is again greater than or equal n plus 2 for this. But now, again, playing the same game of before, we know that f of a sub 0 is strictly bigger than f of a sub 1, that is strictly bigger of f of a sub 2, that is ... greater than f of n, that is greater than, and so on. But again, this is impossible because the set of ordered natural numbers between 1 and f of a sub 0 is finite, but we constructed a sequence of an infinite number of natural numbers that are between 1 and f of a sub 0. So this is impossible, and what led to the contradiction? This hypothesis. So we know that it does exist a natural number m such that f of m is equal to n plus 1. If we suppose that m is strictly greater than n plus 1, this means that m is equal to n plus 1 plus k for a k natural number. But this is impossible because f of n plus k plus 1, that is equal to n plus 1, is greater than f of n plus k, and this means that f of n plus k is in the set 1 ... n, and so from our inductive hypothesis, let me just find it, okay, it is here, we know that if this happens, this means that f of n plus k is actually in the set 1 ... n, but this again means that n plus k is in the set 1 ... n, but this is impossible since n plus k is greater than n. So we got a contradiction, and so m equal to n plus 1 is the only integer such that f of m is equal to n plus 1. So this concludes the proof, and this was everything for this video, and ciao to everyone.